Hello everyone. Today we're presenting UnBound, a high performance solver for the traveling salesman problem. Our key idea is combining a fast C engine with a modern web interface. This is our DA project and we'll walk you through what we built. The traveling salesman problem is about finding the shortest route that visits every city once and returns back. It sounds simple, but it becomes extremely complex as input size grows. Exact solutions take exponential time, which makes them impractical for large inputs, and that's why performance becomes critical. Our system uses a three-layer architecture, a React frontend for interaction, a fast API backend to handle requests, and a C engine for computation. Each layer is chosen for what it does best, that is usability, control, and speed. The core of our system is written in C for maximum performance. It handles all heavy computation using separate modules for generating data, exact algorithms, and approximate algorithms. This keeps the system fast and efficient. We implemented 4 different algorithms. Hellcarp and backtracking gives exact results but are slower. Nearest neighbor and Christophidis are faster but approximate. Each has its own trade-off between speed and accuracy. We also use parallel processing to improve performance. So instead of checking solutions one by one, the work is divided across multiple CPU cores. This significantly reduces execution time. The sandbox allows users to experiment. You can input data, run different algorithms, and compare results instantly. It helps in understanding how each algorithm behaves. The performance lab shows how algorithms scale with input size. Each algorithm becomes slow quickly, with approximation methods remain efficient. This clearly shows the trade-offs. We also support the batch processing. Multiple inputs can be solved together and results are generated efficiently without delays. So apart from the web app, we built a command line tool as well. It allows users to run the solver directly, supports to solver directly, and supports standard data sets. This makes the system flexible and practical. We handled issues like edge cases, memory management, and performance limits. We also ensured the system remains stable and efficient for different input sizes. The key takeaway is that there is no single best algorithm. The right choice depends on input size, time, and accuracy needed. UnBound demonstrates how to balance theory with real-world constraints. Thank you.
Alright everyone, so now in this particular section of the video, I, Deepanshu, will show you how the project is working through a demo. I will navigate you towards various features of the project and how actually you can use it. So let us begin. So now we will try to run this particular backend server and then we will run the npm. So for this we will write the simple command at python m uvcon. The file is an API, so API main application load. So you can see applications is completed. Now we have to run the front end. So I've already come in the front end part of the UnBound. In this one, I will run a simple command npm run dev, and yeah, this is working. So let us see. All right, so this you can see is the front end part. All right, so this you can see is the front end part. So we have 3 different modes here. This mode is for when you have to calculate only one value, like we have one problem. This is for you have to, when you want to like see, when you want to see how these behave for different ends. And finally, this one is for the, if you have text file that contains multiple questions for the TSP, then you can use it. So for the first one, you have 2 options again. You can either simply just give the number of cities and it will generate a random values, and on that it will try to solve it. Or you have the custom where you will paste your own matrix and you can use it. So let's see first the custom one. So let's say I paste this one. This is a flattened matrix. Basically you send the 1D array form of the 2D matrix, and let's run it. So you can see here I took the n equal to 11. This is the matrix, you can see, and these are the algorithms and their representations. So this was a base graph that we took. Then you have 2 different uh, two different things. The first one is the approximations. For that you have the greedy and you have the Christophites, and then you have the another one which is the exact algorithm, which is the held cap, and second one is the parallel backtracking. For each of them you can see the cost, the the time of execution, their time complexity, and the graph, and finally the backtrack path that it is proposing. Same for this one also, same for this one also. The only thing we can note here is that both the backtracking and the held gap dp, they both are giving the same cost. And you can see here the greedy ones, they are not giving the same cost. See, 235, it is different from this one. All right, let us now run a random one. So let's say I take some value, let's say 11, and I execute it. You can see here similar thing. It took this matrix and you have this particular value held cap. It took 1 millisecond, and you can see Christopher it's only took upon about 124, or maybe you can say about 12 microseconds it took. Okay, next one is the performance tab. You can see the performance here. So let us run it. You can change these values and you can also run it for it. Every time it will take some random values and check if it is working or not. So let's say this one, this is the execution time versus the n graph. So for you can see for lower ends till 11, they are literally having similar times, but as n increases, you will see that they are giving different values. The Christophites and all, Christophites and the greedy, basically the approximations are still hugging the zero, but other one they are increasing. This is the ratio, the cost ratio, basically just to see how the answers are diverging. So initially they are almost same. Sometimes they are not same. You can see here 0.9 ratio. Here you can see 0.8 ratio at a very large amount of n. And this is for the timing ratio approximately and the exact. So you can see this will be approximately zero, like they are insanely faster. And here you will see the ratio changes. Now finally you have the batch pipeline, basically text file. So let us put some text file here. Let me give this text file. As soon as I uploaded it, you can see the answer is here. The three questions are there. All three are submitted. Okay, you can upload more and it will start doing it. So this was all about this particular project.